So in the last example, we found the position at 15 seconds and then we graphed the position from 0 to 25 seconds. In this example, we are going to now find the velocity at 15 seconds and then later find the acceleration. So remember, to find velocity from these position equations, all we need to do is take the derivative, because we know that velocity is the change in position with the change in time. And remember that the derivative is the change. So, in order to take the derivative, we get velocity in the x direction. We take this 2 right here. We multiply that 0.31 times 2. We end up getting a negative 0.62. And then t, and it's just t because we subtract 1 from that 2. So it's t to the first power. And then plus, all we get is 7.2 for the derivative of 7.2t. And then 28 is just a constant, so the derivative of a constant is 0. So doing the same thing for the y direction, we take this 2, multiply 0.22 by that 2, and we get 0.44 times t plus, nope, not plus, minus 9.1 is the derivative of 9.1t. And again, 30 is a constant, so the derivative of that is 0. So now what we want to do, we now want to find the velocity at 15 seconds. So velocity in the x direction at 15 seconds is going to be 0.62 times 15 seconds plus 0.72, sorry, 72. And then we end up getting a negative 2.1 meters per second for the x direction. And then for the y direction, it's going to be 0.44 times t minus t, which is 15, minus our 9.1. And we end up getting, in the y direction, the velocity is a negative 2.5 meters per second. Now I'm going to put this both in the unit vector notation and the magnitude angle notation, just like we did before. So unit vector notation, the velocity vector is equal to a negative 2.1 meters per second, I hat, minus 2.5 meters per second, j hat. And notice how you can put the negative sign inside the parentheses or outside, like subtracting. It's totally fine. Both legal. Both are okay. Now for magnitude angle, we know that the x component is negative and the y component is negative. So that's how we're going to draw our velocity vector. The x component is our negative 2.1 meters per second. Y component is 2.5 meters per second. And so now we want to find this velocity vector magnitude. So to do that, we use Pythagorean theorem. Square root of 2.1 squared plus 2.5 squared. If you can hear my husband whistling, yes, that is him in the background. And then in order to find the velocity vector, we just do this in our calculator. We get 3.3 meters per second for our velocity vector magnitude. And then the angle, we get a inverse tangent of 2.5 opposite over adjacent 2.1. And this angle ends up being 30 degrees. Okay, so there's our unit vector notation and magnitude angle notation. Now, if we draw this into our actual plot that we already plotted the x and y path on, we can see that the velocity, this is our x component of that velocity and the y component of the velocity. And then you can also see that they have plotted the actual velocity vector. And remember, whenever we have a path like this, that velocity vector is the direction of motion. So really what it is it's always going to be tangent to that path. So at that point, at that 15 seconds right there, the velocity vector is tangent to the path, which you can see right there. Okay, let's look at the acceleration here. So again, just like velocity is the derivative of the position function, acceleration is the derivative of the velocity function. So taking the acceleration or the derivative of the velocity function, so in the x direction, we have just a negative 0.62 meters per second squared. And in the y direction, we have just a 0.44 meters per second squared. Easy peasy. So again, you can see that they've graphed it on the side right here. So our x is this negative 0.62 and the y is a positive 0.44. Now you can see here that the acceleration is actually directed toward the center of this arc right here, which is because it's actually helping that rabbit change its direction. Remember, acceleration is a change in velocity that could either be speeding up, slowing down, or changing direction. So here what that acceleration is doing is it's actually changing the rabbit's direction, and that's called a centripetal acceleration. We will talk way more about that in the future when we talk about circular motion. All right, so let's find acceleration in unit vector notation in magnitude angle like we did before. So in unit vector notation, the acceleration vector will be that negative 0.62 meters per second squared I hat plus 0.44 meters per second squared J hat. So that's our unit vector notation. And then magnitude angle notation, again, we know that this is a negative. I'm going to redraw that actually. It's a negative x component and a positive y component. So our x component is that 0.62, y component is 0.44, and so the resultant vector is going to be right there from the tail of the origin to the tip of the second vector. So again, finding our magnitude, we're going to use Pythagorean theorem. We get the square root of 0.62 squared plus 0.44 squared. We get acceleration is equal to 0.76 meters per second squared. And this is the magnitude of our acceleration. And then to find that angle, it'll be that angle right there. We're going to use the inverse tangent of opposite 0.44 over, not hypotenuse, I keep wanting to say that, opposite over adjacent for the tangent. If you wanted to use opposite over hypotenuse, you could use the inverse sign, that works too. The angle ends up being 35.36 degrees. So there's our acceleration in both unit vector notation and magnitude angle notation.